Hi everyone, my name is Shuichi Hirahara. Today I'm going to talk about non-adaptive security reductions of heating set generator. This is joint work with Osamu Watanabe. The main question we are concerned with the average case complexity of NP. One of the central questions in the theory of average case complexity is whether we can base the average case complexity of NP on the worst case complexity. For example, let's consider the following question. Assuming that NP is hard in the worst case, can we prove that NP is hard in the average case as well? To be more specific, assuming that NP is different from P, can we prove that dist NP is not contained in average P? Here, dist NP is an average case version of NP, and this class consists of a distributional problem such that the problem L is in NP and we consider a distribution on it which is an efficiently sampled distribution. Average P stands for average case polynomial time algorithm, and there are several equivalent definitions of average case polynomial time algorithm, but here we consider the following notion of average case polynomial time algorithm. We say that a distribution problem is in average P if we can design a polynomial time, if we can design an algorithm M such that M computes L on every input, and the expected running time of the algorithm M on input X raised to the power of epsilon is bounded by order n. For some technical reason, we have epsilon inside of the expectation, but this basically says that the running time of the machine is bounded by a polynomial. There has been a long line of research which explains why it is difficult to resolve this open question. There are at least three types of barriers which explain the difficulty. One is a relativization barrier, which was presented by Impagliazzo. The second one is that there is no hardness application procedure which is computable in the polynomial time hierarchy. A standard proof technique is to construct a hardness application procedure which takes a worst case hard problem and convert it to an average case hard problem. But we can't hope to use such a procedure as excluded by Viola. And the third types of barrier is what we call limits of black box reductions. And this is our main focus of this work. Let's consider the following naive approach to prove the implication. Namely, let's say we would like to prove that assuming that NP is easy on average, NP is easy in the worst case. In order to do that, it suffices to construct a reduction that looks like this. We'd like to design a polynomial time reduction that solves the problem L, which is some NP complete problem, and the reduction makes a bunch of queries to average case algorithm that solves the some distributional NP problem, and given that answer, we would like to solve some NP complete problem in the worst case sense. Usually, when we design a reduction, we can design a black box reduction. Here we say that the reduction is black box if the reduction solves the problem L given any oracle that can solve the average case problem. So the point is that we don't care about efficiency of the oracle. Unfortunately, Bogdanov and Trapezian showed that we can't hope to construct a black box reduction. Specifically, under plausible assumption, they showed that there is no such randomized polynomial time non-adaptive reduction. unless L is contained in co-NP/poly. In our case, L is NP complete problem, therefore it is quite unlikely that NP is contained in co-NP/poly. Therefore, we can't hope to construct such a black box reduction. So far, we have explained the case of NP, but in fact, the corresponding question is open in the case of pH as well. Specifically, the following is an open question. Assuming that pH is different from P, can we prove that pH is easy on average? This is actually easier open question than the previous open question. Well, both of the conclusion and the hypothesis are weaker than the previous question, so it is not immediately clear, but the hypothesis is actually known to be equivalent to NP different from P, so the only conclusion is weaker, so it is an easier question than the previous open question. So before resolving the open question about NP, we should first resolve this open question. When it comes to this open question, we have rather poor understanding on why it is difficult to resolve this open question. We do know that there is no hardness amplification procedure computable in pH, so we can't use hardness amplification procedure, but we don't know whether there is a limit of black box reductions for resolving this open question. What we show in this work is to present the first limit of black box reduction from NP to some form of this pH. Specifically, I'm going to consider the problem of avoiding pH compatible heating set generator, and then I'm going to present the limit of black box reductions. Before I explain that, first let me explain why previous limits of black box reduction fail to explain the difficulty of resolving this open question. Let's try to apply the previous limits of black box reduction to the case of pH, and then I will explain why we can't apply it directly. So the goal now is to prove that, assuming that pH is easy on average, let's say the second level of polynomial time hierarchy is easy on average, we would like to show that NP is easy in the worst case sense. Now, in order to prove that, if we can prove a reduction that looks like as follows, we can prove this implication. We would like to design a polynomial time reduction that solves some NP complete problem that makes a bunch of queries to average case algorithm that solves some distributional NP to the NP problem. Now, we can exclude such a reduction by just generalizing Bogdanov and Trevisan under some condition. We can show that there is no non-adaptive randomized polynomial time reduction unless L is contained in co-NP to the NP/poly. But the problem is that this condition is always true because NP is contained in co-NP to the NP. Therefore, if L is NP complete problem, we can't deduce any interesting consequence from this theorem. Instead, what we do in this work is to restrict distributional pH problem as a problem of avoiding a heating set generator, and then I will going to present limits of black box reductions. A heating set generator is a fundamental notion in the theory of de-randomization. But here, instead of de-randomization, I'm going to use a heating set generator in order to construct average case halo question. Let's recall the notion of heating set generator. A function h is called a heating set generator if the seed length of h is strictly less than n, which is out of the ranks. And moreover, for any polynomial time algorithm A such that A accepts most input, let's say a quarter of inputs, then there is some y which is in the image of H and accepted by the algorithm A. Now, if we can construct such a secure heating set generator, and let's say the heating set generator is computable in pH, then we can construct an average case hard problem in pH. This can be shown as follows. We just take the distributional problem of testing the membership in the image of H under the uniform distribution. Clearly, the image of H is the problem in this pH, so this defines an average case hard problem. So, in order to present an average case hard problem, we can construct a heating set generator. In fact, in my subsequent work, I was able to prove the converse reaction of this fact. So this is a quite general approach for showing average case hardness of pH. To summarize, here is a general approach for basing average case hardness of pH on the worst case hardness of pH. We would like to construct a black box reduction which solves some NP complete problem, L, and the reduction makes a bunch of queries to some average case algorithm that solves the problem of testing the membership in the image of H under the uniform distribution, which is a problem in this pH. Here we take a heating set generator which is computable in pH. The main result of this work is to show that it is unlikely that there is such a black box reduction. Namely, let H be any candidate heating set generator, which is just a function. We can show that there is no such randomized polynomial time nonadaptive reduction unless L is in co-NP/poly, which is quite unlikely if L is NP complete problem, or otherwise the seed length must be quite close to n. So, and if we can prove that there is a black box reduction, it is likely that it's because the seed length is quite close to n. More generally, we can prove the following theorem. Let's take any function h which extends its seed by at least a constant fraction. And let's also assume that there is a reduction from L to any oracle that avoids H via randomized polynomial time nonadaptive reduction. Here we say that the oracle avoids a heating set generator if it violates the condition of H being a secure heating set generator. In that case, we can simulate the reduction in NP/poly intersect co-NP/poly, and we also have an upper bound of S2 to the NP. Moreover, if we know that the H is computable in exponential time, we can put L in AM intersect co-AM. Previously, Goodfriend and Burton showed that there is an upper bound of BPP to the NP, but our result improved the result from BPP to the NP to AM intersect co-AM. In the rest of my talk, I'm going to present a proof idea of main result. So first, I'm going to clarify the definition of avoiding. We say that an algorithm A avoids a function h if A accepts at least a quarter of inputs, and moreover, A rejects every string y which is in the image of h. Now, in order to prove the main result, let's, by assumption, there is a black box reduction from a problem L, which is a problem we would like to solve, to any algorithm, any oracle A avoiding a function H. Namely, for any input X, M can compute L with high probability given any oracle A avoiding a hit function. Our goal is to simulate this reduction in AM intersect core AM. Since this is a randomized non-adaptive reduction, we can take a distribution of queries, which we denote by Q sub X. This is a distribution of queries that M makes on input X. Pictorially, we are going to consider a function H whose image is quite small compared to all the n-bit strings. So that the image of H looks like this, which is quite tiny compared to all the n-bit strings. Now we have a reduction M which makes some queries. In order to make the exposition simpler, we are going to make two assumptions. One is that every query that M makes is of length n. This is basically without loss of generality, but for simplicity, let's assume that we are focusing on n-bit string for some integer n. Now we also make an unrealistic assumption, which is that the support of the query is quite small compared to 2 to the n. This is not always the case because we can make all the n-bit strings with non-zero probability. But for simplicity, let's consider this easy case. In this case, it is easy to simulate the reduction in BPP. How do we do that? Well, we first define an oracle A, which looks like this. A is all the n-bit strings minus the support of all the queries minus image of H. The reason why we define the oracle A is that we can make sure that A avoids a function H. The reason is that there is no intersection between A and image of H. And moreover, the size of A is quite large. So A avoids H, which means that since the reduction is black box reduction, we can make sure that the reduction M given the oracle A works correctly. Now we are going to simulate this reduction in BPP. We can easily simulate this reduction because there is no intersection between support of the queries and the oracle A. So in order to simulate the reduction, we can just answer any query of the reduction M as with saying that it is no instance. Therefore, we can simulate it in BPP. So in this case, we can easily simulate the reduction in BPP. Now, let's consider the general case. I'm going to remove the simplifying assumption. In general, it can be the case that the reduction makes every n-bit string with non-zero probability. In that case, the support of queries might be all the n-bit strings. In this case, we can't use the trick that we used before. Because if we define the oracle A in the same way as before, we can't make sure that A avoids H. But still, we can use a similar approach by relaxing the condition with support. So the problem with the support is that we consider every string which has non-zero probability of being queried. Instead, I'm going to only consider a query which is often queried by the reduction. Specifically, this notion is called alpha heavy, and we say that a string Q is alpha heavy if the probability that is queried is at least alpha times 2 to the minus n. Here we think of alpha to be some large parameter. And by a simple argument, we can show that the number of alpha heavy strings is much smaller than 2 to the n. So we have a similar situation as before. So we can define a new oracle A as all the n-bit string minus image of H minus alpha heavy. So the difference between the previous case and this case is that instead of support of the query, we consider the relaxed notion of alpha heaviness. As before, we can prove that A avoids a hitting set generator H. Therefore, we can make sure that the reduction works correctly given the oracle A. Therefore, it remains to simulate this reduction in M intersect core AM. But unfortunately, it is unlikely that we can directly do that because we can't decide whether a query Q is in the image of hitting set generator, because in general, hitting set generator might be not computable. In order to deal with this issue, I'm going to modify the definition of oracle, and I'm going to define a prime, which is defined as the complement of alpha heavy strings. Now, if we define a prime in this way, a prime might intersect with the image of hitting set generator, so we can't make sure that a prime avoids H in this case. But still, we can prove that M to the A prime works correctly by using the following fact. We can prove that M can't distinguish A and A prime. The reason is that if you consider any string outside alpha heavy instances, the string is rarely queried by the reduction. Therefore, if we change the string a little bit, that doesn't affect the correctness of the reduction. To be more specific, the image of H intersect A prime is rarely queried, so we know that M to the A works correctly, therefore M to the A prime must work correctly as well. Now, in order to complete the proof, we need to simulate M to the A prime in M intersect core AM. In order to simulate the reduction given the oracle A prime, in the previous work, Goodholland and Burden simulated the reduction in PPP to the MP by using approximate counting. Our main technical contribution is to improve the simulation protocol to AM intersect core AM. The main ingredients are the following previous protocols. One is the Feigenbaum-Fortnow Protocol, another is the heavy sample protocol, and the last one is the lower band protocol. Let me explain how we combine these three protocols. The Feigenbaum-Fortnow Protocol is an AM intersect core AM protocol that can simulate any non-adaptive reduction, assuming that the following two conditions are satisfied. The first condition is that the oracle A can be solved in AM. In our case, we can do this by using the lower band protocol. So the first condition can be satisfied. The second condition is that there is an advice P star which approximates the probability that the query is a positive instance of A. We can compute such an advice efficiently by using a heavy sample protocol of Bogdanov and Trevisan. To conclude, we can simulate the reduction by combining all these three protocols, which complete the proof of the simulation. To conclude this talk, we have presented the first limit of black box reduction, which can be given by presenting limits of non-adaptive security reductions of a heating set generator. Thank you for your attention.